Hello everyone, welcome to this video. So here we have the grade 12, November 2022 paper. It's Physical Sciences paper 1, 150 marks, 3 hours. If you want to download the paper, just check the description below. Which one of the following combinations consists of only scalar quantities? Okay, so can you remember in grade 10 we learnt about scalar and vector. Now scalar is something that only has magnitude, whereas vector has both magnitude and direction. Okay, so some examples of scalars would be time, mass, distance, whereas things for vectors would be things like weight, acceleration, velocity, displacement, force, and so on. Some more examples here would be speed as well as energy. All of those are scalars. So it says here, which one of the following combinations only consists of scalars? So it won't be this one, because there they've got velocity. And velocity is a, where did we say? Here, it is a vector. So it won't be that one. What about this one? This one looks good. It's got time, distance, and speed. So that would be the answer. Why won't it be C? Well, it's got acceleration. And why won't it be D? Well, it's got all three of those are vectors. Okay, so the correct answer here will be B. The acceleration due to gravity on Earth is g. Which one of the following represents the acceleration due to gravity on a planet that has twice the mass and half the radius? Okay, so this question is all about Newton's law of gravity. Now, we know that there's this formula. Okay, now we also know that this force over here is force of gravity. Force of gravity. Now, how do we normally calculate that? If you were busy with a Newton's law kind of question, how would you find Fg? Well, you would just say the mass of the object multiplied by gravity. So I'm going to change this F to that. Okay, so remember this is the mass of the object. And then I'm going to pretend that one of these is the object and one of them is Earth. So let's say object and Earth. Okay, so then we're going to get a formula that goes like this. Object and Earth. And then when they're just talking about the radius of the Earth and acceleration due to gravity on Earth, it means that you have a planet where the distance between the center of the planet and the object is also going to be the radius of the planet, because you see how it is. But if there was an object somewhere over here, then the distance between them is not going to be the radius of the planet. But when the object is directly on the surface, then that is the radius. So this part here, I will call this radius of Earth. Okay, now check this out. This mass is the object and this mass is the object. So they are going to cancel each other out, okay? We're going to cancel them out. So we're just going to go boom and boom. And then we end up with a nice formula that goes like this. And we actually get these formulas on our formula sheet. So here's the one that we started with, okay? And then we modified it to become that. Now obviously they're writing it a little bit weird with the g in the front like that, but it's the same thing. Gm over r squared, gm over r squared. Okay? So this is now the formula that we can use to analyze this question, because what they've said is that the acceleration on Earth is g. Now they want to know what is going to happen to the g on a planet that is twice the mass of Earth. So we're going to change these numbers now. So this g stays the same. Now instead of saying mass of Earth, we're going to say 2 times mass of Earth. Okay, because it's double the mass of Earth. And then for the radius, it's half. So we're going to say half radius of Earth. and that's squared. Now, what we're going to do is we're going to take this 2 to the front, so we're going to end up with 2g m Earth over, now a half to the power of 2 becomes a quarter, so we're going to say a quarter r Earth to the power of 2. Okay, so we know that this part here is what we had originally, and that was equal to g. So I'm going to replace all of that now with g. Okay, so just like that. And so then what we can say is we can just say 2 over a quarter g. And then you can just go type this on your calculator and you would end up with 8 g. So that's going to be d. A ball is projected vertically upwards from the ground and reaches its maximum height after a while. Ignore the effects of air friction. How will the acceleration and total mechanical energy of the ball at its maximum height compare to that immediately after it was projected? All of this should stay the same. So the answer is going to be A, but let me explain. So we know that if you have a ball down here, and if you throw that ball upwards, while that ball is busy going upwards, if you had to draw a free body diagram, what forces are acting on it? Well, there's only gravity pulling it down. Some of you are, but yeah, Kevin, isn't there a force making it go up? No, there isn't. There was someone who threw it originally, and at that moment there was a force. But as soon as the ball leaves the person's hand, it will begin to slow down because the only force acting on it is gravity. Okay, the force of gravity. When it reaches the very top, what forces are acting on it? Only gravity. Now, that gravitational acceleration never changes. So, it says, how will the acceleration at its maximum height compared to immediately after it was projected? It'll stay the same. Okay? Now, let's talk about mechanical energy. What is mechanical energy? Remember that mechanical energy is the combination of kinetic energy plus potential energy. So when there's no friction or anything like that, if you take an object like a ball, and if you throw that ball upwards, the potential energy is going to increase because it's gaining height. Remember, potential energy is mg height. But the kinetic energy will become less because that's half mv squared, and as the ball goes up, the velocity decreases. So the potential energy will increase and the kinetic energy will decrease as the ball goes up. And then when the ball comes down, the kinetic energy will increase and the potential energy will decrease. But the total always remains the same. That is the law of the conservation of mechanical energy. So that will also remain the same. So the answer will be A. A car travels at constant velocity along a horizontal road. A constant frictional force acts on the car. Let's draw that out quickly. So we've got a car going in that direction, for example, but it's going at a constant velocity. They tell us that a frictional force acts on the car, so that would always try to slow the car down, so that's going to be friction. And which one of the following statements about the power dissipated by the engine? So to keep the car moving at a constant velocity, you would need the same force from the engine to keep the car moving at a constant velocity. Okay, so that's your friction, that's your engine force. They are going to be exactly the same so that the car can move at a constant velocity. Now it says, which of the following statements about the power dissipated by the engine of the car is correct? The power is, okay, so we know that power could be calculated as work divided by time, but it's also equal to force multiplied by average velocity. So if we just look at this one, power is equal to the force of the engine multiplied by the velocity of the vehicle. Now, the force of that engine has to stay constant so that it can balance the friction that is constant. And the velocity is going to be constant because they tell us that. So this whole value is going to remain constant. So the answer is D. Whoa, this looks like a lot. Block X is placed... Oh, by the way, this is only a 2 mark. It's just a normal multiple choice. Okay, block X is placed on a horizontal table and is connected to block Y by a light, inextensible string over a frictionless pulley. A constant frictional force acts on block X while it is being pulled to the right. Okay, so it's being pulled to the right, and so the friction force would be acting in the opposite direction. So there's your friction force. P, Q, R are points in the table such that the distance from P to Q is equal to that from Q to R. Okay, so from P to Q is the same as from Q to R. Okay. When block X, I just want to quickly see something here. Constant friction. When block X reaches point Q, the string is cut, and block X continues to move towards point R. Ignore the effects of air friction. Okay, so this block was on its way that way. And then when it gets to this area here, they cut the rope. But because of its initial momentum, or you can think of its inertia, it will keep going to the right. Okay? It'll keep moving for a small amount of time. Now, it won't move forever because of friction, which we have. Now it says, consider the following statements. The work done by the frictional force acting on block X is greater when the block moves from point P to Q than when it moves from Q to R. Well, let's look at it from a formula perspective. So we know that work is equal to force, displacement, cos theta. So we know that when it goes from P to Q, there is a certain force, displacement, and then cos theta. Now when it goes from Q to R, the friction force is not going to change. Some of you are like, yeah, but Kevin, doesn't the friction become less when it goes slower? Because now when we get here, the rope gets cut. So won't it slow down? Yes, it will slow down, but the friction doesn't become more or less because friction is equal to the coefficient of kinetic friction multiplied by normal force, and these two do not change depending on how fast the object moves. So this parameter will remain constant. This will remain constant because this distance and this distance is the same, and then this will always be cos 180 when we're talking about friction. So this statement is wrong. This is wrong. It says both the momentum and kinetic energy of the block X decreases when the block moves from Q to R. That is true, but let me show you why. We know that momentum is P equals to mv. Now, can we agree that when the block is going from Q to R, it will slow down because it only has friction acting on it and it no longer has this block that's pulling it? Okay, so this value is going to decrease. Then kinetic energy is equal to a half mv squared, and the v is going to decrease. So both momentum and kinetic energy will decrease as we go from Q to R because the block is going to slow down. Because the only force acting on it from Q to R is friction. Okay, point number 3. So this point is correct. Point number 3, the total mechanical energy of block X remains constant when going from Q to R. That is not correct. Mechanical energy is only conserved when there are no non-conservative forces like friction and applied forces. If there are friction forces, then mechanical energy is not conserved. And I'll show you that mechanical energy is potential energy plus kinetic, and potential is mgh, kinetic is a half mv squared. So if you compare the mechanical energy here, you would use this formula, and if you had to compare the mechanical energy here, you would also use this formula. Can we agree that this value here is not going to change because the height is not changing? The only thing that is changing is this. And we just saw from point number 2 that this parameter is going to become less. So the mechanical energy will not remain constant, will not stay constant when going from here to here. So this is wrong. So the only statement that is correct is number 2. So the answer is B. The light emitted from a distant star contains spectral line X of frequency F. The spectral lines of the star, when observed on Earth, are red shifted. Okay, so this is the whole red shift, blue shift. Which one of the following combinations of the spectral line is correct? Okay, so let's have a look. So what they're telling us is that we've got planet Earth. Did they say Earth? Yes. Okay, so here's Earth. Okay, Earth. We've got a star. Ugh, I can't even draw a star. Okay, there's my star. We know that stars emit light. Now, light travels as energy, and we can measure the frequency. Okay? So, if the star was not moving, then you would simply measure its real frequency. But because the star is moving, we've got the Doppler effect happening. Now, I'm going to show you 2 scenarios quickly. Number 1 and number 2. So this is number 1. If star moves towards Earth. And then number 2, if star moves away. So if the star moves towards Earth, we need to think about the Doppler effect. You can think about if this star is coming towards the Earth like this, it's going to cause these waves to compress. So they're going to be more like this. That means high frequency. Okay, so we can say that frequency increases, and we call that a blue shift. I'll explain how it's a blue shift shortly. Okay, now if the star moves away, so if it goes that way, then it stretches the waves out. So the frequency decreases, and we call that a redshift. I'll explain that now. So we know that in our color spectrum there are, I think it's 7 main colors that we look at. 1, 2, 3, yeah. Okay, now red, orange, yellow, green, blue, indigo, and violet. So red, you need to know, is more of like a lazy kind of wave. Whereas blue, violet, that's more of an energetic, high frequency wave. So, if the star is going away, we said it makes a more lazy kind of wave, so we call that a red shift. And when the star is coming towards the Earth, then we get a more compressed kind of wave, and we call that a blue shift. So they tell us here that the spectral lines are red shifted. Oh, okay, so they tell us that we're red shifted. That means that we are moving away. So this can't be right and this can't be right. So D and B cannot be correct. Now, if you are red shifted, the frequency should decrease. And that's there, smaller than F. So C would be the answer. Remember that this star is releasing its own frequency. But depending if the star is going away or towards will cause the observed frequency on Earth to either be more or less. And that's why they've called it the observed frequency. A proton and an electron are a distance r apart. Okay, so let's quickly draw that. So we know that a proton is positive and an electron is negative. And they are a distance r apart. Okay. The magnitude of the electrostatic force that they exert on each other, okay, is F. Okay, we know force is equal to K Q1 Q2 over R squared. Which one of the following graphs shows the relationship between F and R squared as the proton and electron approach each other? Well, the way that you work out the shape of a graph is you look at the y-axis, which is F, and you look at the x-axis, which is R squared. If the one is at the top and the one is at the bottom, that's an inverse relationship. And so the answer is going to be, okay, well now it could be it could be, or no, when the one goes up, the one goes down, so it has to be C. Let me quickly explain though. If you had another relationship like, let's say we had R squared K G, I'm just making up a formula. If both of them are at the top like that, then you get a linear relationship, and then it would look like that. But as soon as you have one at the top and one at the bottom, then you get a inverse relationship like that. An example of that is actually a hyperbola. A hyperbola, for example, is 1 over x minus 2 plus 4. See how you've got the y at the top and the x at the bottom? Now, what does a hyperbola look like? Well, a very basic hyperbola does that. And then obviously it has this other side, but we don't look at this other side in physics. We're just looking at that one side. And there you can see it. The EMF of a battery is that, and its internal resistance is R. The battery is connected to 3 resistors, okay, here they are, 2 parallel and then 1 in series, and 4 voltmeters. The resistance of the conducting wires is negligible, blah, 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 while the voltmeters, okay. Which one of the following equations represents the reading on voltmeter V1 in terms of the readings on the other? This is a good question. Okay, so I've explained this in detail in many of the electricity videos that we've done, but what you must remember is that in parallel, your voltages are the same, okay? So V3 is the same as V4. And to know what the voltage is for this part, you just choose one of them. You don't choose both of them. So, okay. And then another thing is that, so those are in parallel, so we just choose one of them. And then for all the others, for all these voltages now, they must all, when you add them together, it must be equal to your V1. So what I mean is the following. V1 will be equal to V2 plus V3, or you could say V1 is the same as V2 plus V4. So for this part over here, you only choose one of the voltmeters, okay? And your external voltage must always be equal to those added together. If we had another voltmeter over here, like a V5, then you would say that V1 is the same as V2 plus V3 plus V5, or you could use V2 plus V4 plus V5. So let's see if they have any of those. Or there they've got V2 plus V3. An AC generator consists of a coil which is rotated in a magnetic field. The EMF time graph for one complete rotation is shown below. Okay, so here they show us one complete cycle. Then it says, if the speed is now doubled, which one of the following graphs is correct? Okay, so don't even look at these. What you need to understand is that EMF is equal to, we've looked at this in electrodynamics. Now, if you double the speed, what do you do to this value? Well, you half that value. Because remember, when you do something faster, the time becomes less. So if you double the speed, you half this value. And by halving this value at the bottom, you're causing this number to become larger. You're actually going to cause this number to double. So we should expect that these are going to go up to 300. Okay, it's going to go up to 300 and down to minus 300. But we should also expect that it won't take 0.2 to be able to make one cycle. Because we're going twice as fast, we should expect that this number is now going to become 0.1. Now we can go look, and we can look for the 300s here and here. So this is wrong and this is wrong. But then we look at the time, and this is 0.2 and this is 0.1. And so our answer must be C. White light is passed through a cold gas and then through a prism as shown below. A line spectrum is observed on the screen. Okay, so I have explained emission and absorption on the Kevin Math Science course. And so I will, but in my explanation in that video, I didn't talk about cold gas. So let me see if I can quickly try to summarize how this works. So we start with white light. Now, what is white light? White light is all the colors combined. Red, orange, yellow, green, blue, indigo, violet, all together. That is called white light. So let's just quickly draw here. We've got a bit of blue, some green, red. Let's do yellow. We can do like a violet-y color or purple. And let's do orange, for example. Okay, so that is white light. Now, what happens is that that white light is shone into this cold gas. Now, in this cold gas, you've got atoms. Okay, I'm going to draw 3 atoms. And inside those atoms, there are electrons. Now, those electrons, well, remember, around the nucleus of an atom, if I draw an atom quickly, here's a nucleus. In the nucleus, you've got protons, which are positive, and neutrons, which are neutral. And then on the outside, you've got energy levels. And in those energy levels, there are electrons. Okay? At specific levels, randomly scattered for various reasons. Okay? Now, what can happen is that, remember, these lights, or the different lights, like yellow, blue, indigo, they have different amounts of energy. Now, if, let's say, for example, we shine the orange light, and let's say that that orange light has just the amount of energy for this electron to gather enough energy to go to the next energy level, because you need more energy as you go out. Okay, you need more energy to go from here to here to here. So maybe, for example, the red goes all the way through. Maybe the red didn't have enough energy, or maybe it had too much energy. It has to have exactly the right amount of energy to allow the electron to go up. So maybe the red did not work. But when the orange was shone, let's say that this electron was able to go up. So this orange light was absorbed by this electron so that it could go to the next energy level. So the orange is not going to go all the way through to the other side of the atom like the red light did, because the orange light was absorbed. Let's take green light, and let's say that the green light went all the way through. That means that the green light had maybe too much or too little energy. It has to have the perfect amount of energy for that specific electron. So if this electron needs 50 joules, then it will only work if the light has 50 joules. Let's say the blue was absorbed by this electron, so that this electron could go up to this level over here. So the blue will not make it to the other side of the electron. It won't be able to go all the way through like that. It was absorbed. So can you see that the red and the green went all the way through, and the orange and blue was absorbed? So then, what light will we see over here? Well, over there, we will see the red, because the red went through. And we will see, what color was it? Green. We'll see the green going through. And so when it goes into this, it goes as, you wouldn't see red and green. It's only when you put it into a prism that it would actually break up. So it would actually be a red. The red and green would actually still be together like that. And then when you put it into a prism, you would see, for example, the red landing up over there and green landing up over there. In all the other places, for example, where the blue was supposed to be, or where the orange was supposed to be over here, you're going to end up seeing nothing. You're going to end up seeing these dark or black bands like this and like this. So what scientists use this screen for is to be able to see what light was absorbed. So we call this, because by looking at this, I can tell you that the red made it through and the green made it through, but all the other colors like orange and blue and all the other colors, they were absorbed. So we call this an absorption spectrum. Absorption spectrum. And so the answer cannot be A or B. And then what is the energy transition? What says here, correctly describe the energy transition of the atoms. Well, they are going from a lower to a higher energy level. You go from a lower to a higher. So the answer is D. Crate P of mass 1.25 kilograms is connected to another crate of mass 2 kilograms by a light string. The two crates are placed on a rough horizontal surface. A constant force of 7.5 newtons acting at an angle theta to the horizontal is applied. The crates accelerate at 0.1 to the right. Crate P experiences a friction of 1.8 and crate Q experiences a friction of 2.2. The first question says, state Newton's second law. Okay, before we state the definition or what it is, let's just quickly think about Newton's second law. Newton's second law is all about F equals to ma. But when you state Newton's second law, get the A by itself. So that's going to give you A equals to F over M. Now, it's actually F net. So Newton's second law tells us that if a net force acts on an object, the object will accelerate. This acceleration, here we go, will be directly proportional to the net force and inversely proportional to the mass of the object. So when this is at the bottom, we call that inversely proportional, and when it's at the top, we call it directly proportional. Now let's go get the proper definition. Okay, so let me just quickly erase this for you. So here we go. When a resultant or a net force acts on an object, the object will accelerate in the direction of the force. The acceleration is directly proportional to the resultant or the net force and inversely proportional to the mass of the object. So remember, when it's Newton's second law, use this equation and then remember to get A alone, and that'll help you to remember the definition of Newton's second law. This question says, draw a labeled free body diagram for crate P, and it's for 4 marks, so there's going to be 4 different things we need to take into account. So there's always going to be gravity. Okay, you could also obviously call that W. There's a normal force. There will be friction, and there will be tension because of this rope. And so there we have 1, 2, 3, 4 forces for 4 marks. Now, I just wanted to quickly show you on the memo, because learners often ask me, can we use different things? So I said you could use FG or W, but you could have used FG, FW, F Earth on P. Goodness me, I've never seen that before. Some people even put the size. You know, if you multiply this by 9.8, it'll give you the size. There's FT, F string for the tension. Okay, that's an Afrikaans one. FT. There's Afrikaans here, I see. FF, FK, FN, normal, F normal, or there's F normal. So you see there's a lot of different ones that you can use, okay? So there's not a one size fits all for these. And this is from the official memo. Calculate the magnitude of the tension in the string. Now, you know how we always usually do these questions, and I always tell you the same thing, right? Do a free body diagram for each object, then do simultaneous, and then solve. But this one is not going to be as difficult because they've given us all the information. They've given us the acceleration. So have a look at this. If we use just on this object here, which is the object P, this is object P. You could say F net equals MA, and then we choose right as positive, and then you would have this one minus this one, so your tension minus your friction, okay, and equals to MA. So the tension we don't know, the friction force, I erased that, didn't I? So they said that was 7, no, a constant friction force of magnitude Oh no, that's something there. The friction was 1.8 newtons and 2.2 newtons. So 1.8 for that one. Its mass is 1.25 and its acceleration is 0.1. You see what I mean? There's only one unknown. Usually they don't give us the acceleration. Then you have two unknowns, tension and acceleration. But in this example, they gave us the acceleration, but then they haven't given us this angle. So it would have been too difficult if they didn't give us this, because then you would have unknown, unknown, and the acceleration would have been an unknown. So you would have had three unknowns. Okay, now if we go solve, we get 1.25 multiplied by 0.1 plus 1.8. Let's write that a bit better. And so if we go work this out, we get 1.93 newtons. And you won't say right or left, because this tension acts right and left. On this object, it acts to the right, and on this object, it acts to the left. And that's why they said magnitude anyways. There's no direction for that. Then this question, for only 3 marks, says calculate the angle. So what I want us to do is I'm going to do a free body diagram on this object. So it will have gravity. So I'm going to just say Fg. It'll have a normal force. It'll have friction. It'll also have tension because of the rope. And then this part here, I always like to break it up into the components, but you don't have to. So I know that this will have a X component, and it will also have a Y component. Actually, I'll say here, applied force in the X direction and applied force in the Y direction. So those are the different forces. Now, I'm going to go use our good old F net equals to MA. I'm going to choose right as positive. So we're only looking in this direction. We're not looking in vertically moving up or down. So we're only going to look at those forces over there, these ones. So we're going to say F applied in the X direction minus the friction force minus the tension is equal to MA. So we're going to say F applied in the X direction, we don't know. The friction on this object is 2.2. Some of you are like, Kevin, should we also include this one's friction? Because surely that one's going to slow this one down. You are correct, it is going to slow it down, but we will see that in the rope tension. That's why there is tension in the rope, okay? And so the tension in the rope that we worked out earlier, what did we get, guys? 1.93. So we'll say here minus 1.93 equals to the mass of that object times the acceleration, which is 0.1. Now we can get F applied in the X direction by itself, plus 2.2 plus 1.93. And that'll give us F applied in the X direction as 4.33 newtons. Now, this is going to help us now, because now we can construct a little triangle over here where we know that this is now 4.33 and we know that this is 7.5. So if I make the triangle a little bit bigger actually, then you've got 4.33, then you've got 7.5, and then you can just close it off, and then we can work out the angle using trigonometry. So we've got the adjacent and we've got the hypotenuse. So we could say that's cos. So we could say cos of theta is 4.33 over 7.5. Get theta by itself. Remember to check that your calculator is in the correct mode. A lot of AP, advanced program, or the AP maths learners, they often message me and they're like, Kevin, I get the wrong answer, but it's because your calculator is in radian mode. At the top of the screen it has an R, but you don't want it to have an R, you want it to have a D for degrees, okay? So just always look out for that, guys. It always makes me so nervous that a learner could go into a test and get that part messed up, and all of the answers relating to trigonometry will be, or any things where you have to calculate angles and using trigonometry, it's going to mess it all up. So this is 54.74 degrees. On the memo, they did say that you can have a range of answers. So if you got anywhere between there, then you are correct. What did we get? Oh yeah, 54.74. So yeah. A ball is thrown vertically upwards from the top of a building of height 25 meters with a velocity of 12 meters per second. On its way down, the ball passes a door which has a height of 1.9 meters and then strikes the ground as shown in the diagram. Okay, so everything's shown pretty nicely over here. We've got a ball that gets thrown upwards at 12 meters per second, and then it comes down and hits the ground. The first question says, define the term free fall. Well, what is free fall? So when you have an object, let's say for example over here, and it's on its way down, if you had to do a free body diagram, the only force acting on that ball would be gravity. If you had to do a free body diagram on the object over there, the only force acting on it would be gravity. If you had to do a free body diagram over there, guess what? Only force acting on it would be gravity. So what is free fall? Free fall is when the only force acting on the object, or it's an object that is moving under the influence of gravity only. And so here we have it from the memo. It says it's the motion under the influence of gravity, or you could have said weight, or you could have said gravitational force only. Okay, and then you could have also said motion in which the only force acting is gravity. So there's a couple of different ways you could say it, so whatever suits you best, but you get the idea of what it is. The next question, this one over here, says calculate the time taken for the ball to reach its maximum height. So we're definitely going to have to use our equations of motion. Now, they're only talking about, they said the time taken for the ball to reach its maximum height. So we're only going to look from here up to there. Okay, so if we just had to draw that out, you've got a ball going like that. So this would be at your initial position, and this would be your final position. We're not going to say this is the final position. Your initial and final are based upon where you are looking at that particular point of the question. So we know that when the ball reaches this position over here, it will momentarily, for a small moment of time, it will have a zero velocity. It will reach a zero velocity, and then it will begin falling again. Okay, so at this position here, we will say that the velocity is 0, and then over here we know that the initial velocity was 12. And what else do we know? We know the acceleration. Remember that when an object is under free fall, the acceleration is always 9.8 meters per second to the negative 2 down. No matter what, guys, even when the object is over here, the acceleration is still acting downwards, okay? When it's over here, over here, over here, it doesn't matter. So we do know the value of A, and they want us to calculate the time. So this would be the best formula to use. So let's go write that down. Vf equals to Vi plus A delta t. You can choose up or down as positive. I'm going to choose upwards as positive. And so we're going to say 0 equals 12 plus. Now, because we're choosing up as positive, but acceleration is always 9.8 down, you must make that a negative and then delta t. Okay, if you ever calculate delta t and you get a negative answer, you have made a mistake. You can never get a negative answer for time. Okay, and so if we had to go work this out, let's take this over to the other side, so it will end up becoming a positive. And then to get delta t alone, you can just say 12 over 9.8, which is equal to 1.22 seconds. 1.22 seconds. This question says velocity with which the ball strikes the ground. Okay, now you have got multiple options. You could go from here to here, or you could go from the very beginning to here. I like to do it that way, but a lot of learners, they like to first do this part and then this part. But what I do is I just go straight from here to here. So this is my initial condition, and this is my final condition. Now, notice that in the first question, I chose upwards as positive. That doesn't mean I have to choose upwards as positive for every single question. You can if you want to, but what I like to do, because this one's going more in a downwards direction, I'm actually going to choose downwards as positive this time. But you don't have to do it that way. Okay, so let's see what we have. We have the initial velocity. We want to calculate the final velocity. We have got the displacement. It'll be 25. Now, some of you are like, yeah, but Kevin, what about this part over here? Don't we have to add that in? But then you're not thinking carefully about what does displacement actually mean. And I see this problem many times. So remember that these values are not distances, they are displacement. So remember that if you and your family go driving on a road trip like this, like this, like this, then to calculate the displacement, you simply look at how far is it from here to here in a straight line. So you just measure that distance over there. Okay, you don't look at the entire pathway that is traveled. That is called distance, but we're not looking at that. We're looking at displacement, which is the distance, which sounds like I'm contradicting myself, but it's only the distance from here to here in a straight line. That is what displacement is. So if this ball goes like this and goes like that and ends up over here, well, the displacement is literally from the starting position, which is here, to the ending position as a straight line. And that is why I said 25. Okay, so don't confuse displacement and distance. So we have got the displacement. So, and then what do they want? The final velocity. So the best formula would actually be this one now. Now some of you might want to use y. It doesn't matter, it's the same thing. They don't mind on the memos either. So we're looking for this. We've got the initial. We've always got acceleration because it's always 9.8 down. And we've got the displacement. So let's go write down our formula. For this one, I'll choose down as positive. But you're more than welcome to keep up as positive. It doesn't matter. But just don't feel that you have to choose one direction for the whole question. Okay, so the initial velocity is 12, but it's negative 12 because it's going up, but we've chosen down as positive for this one. For my acceleration, I'll keep that as a positive because we've chosen down as positive and acceleration is always down as positive. Okay, and then what else? Oh, the displacement. Now here's where learners often make mistakes. Displacement can have a negative or a positive. So all you do is the following. You look at your starting level. So this is your start level. And this is your ending level, or your finishing position, or your final. Let's rather call it final. That sounds better. Now, is your final position above or below? Well, your final position is below. So even though the ball first went up like this, overall, did it end up below or above? It ended up below the starting position. So it ended up going down overall. So because we chose down as positive and the object does end up going down overall, we don't worry about the fact that it first went up. We're just looking at the starting and the ending. Then we can say the displacement is positive 25 because we chose down as positive and the object did end up going down. Okay, and so now we can just go type all of this in. Okay, you should get 634. I've got something very interesting I want to explain to you guys. For those of you that chose upwards as positive, because you would still get a positive answer. And so you might think, oh, so is the object going up? I'll explain that to you now. It's something to do with this, this formula specifically. So, okay, so if we had to go take the square root of 634, then we get 25.18 meters per second. And we'll say down. Okay, let me now explain for the learners that chose up as positive, which is nothing wrong with that. But the problem is you're also going to get a positive answer. Then you're going to maybe think your answer means up. So let's try it. It's one of the weird parts of vertical projectile motion. So now we're choosing upwards as positive. So we're going to go VF squared equals to the initial, which is 12. Now it's a positive 12 because we are going up. Plus acceleration is now negative. And displacement is now negative. Why? Because we chose upwards as positive, but the object is ending below its starting position. Now, if you had to go work this all out, you're going to get exactly the same answer. Now you might say, oh, so I chose upwards as positive, but now I'm getting a positive answer. So does that mean up? And this is the one formula that sort of contradicts what we've learned. The reason is that this formula can never give you a negative answer, because this part's always going to be positive, and these two are always going to go together. Okay, you see how here they were both positive, here they were both negative. So you're always going to get a positive answer for this one. So you just have to rather look at the diagram when giving your answer like that. Okay, that's quite a weird one. It doesn't fit the normal scenario, what we've been taught. If you choose up as positive and you get a positive answer, that means up. You have to look at the context of the question. Now, you can get different answers. So we got 25.18. But on the memo, I'll go have a nice look for you now. But if you were a student that used a slightly different technique, on the memo, there's literally like 9 or 10 methods you could have used for the first question. And that would have given you a slightly different answer over here, which would affect this answer over here. So you were allowed to get anywhere between 25.03 all the way up to 25.59. If you got anywhere between there, then you're fine. This question says, what is the time that it took the ball? So what is the time for from the top of the door? Wait, what? Time it took the ball to move from the top of the door to the ground. Oh, okay. So from here to here, how long was that time? Okay. Different ways of doing this. I immediately think, I think I've got an idea of what I want to do. What I'm going to do is I'm going to see how long does it take the ball to go from the starting position up to here. Okay, so I'll call this top of door, and then this will be ground. So my first step is how long from the start to top of door. Okay, so I'm never going to look at this position. You can if you want to, but I just keep it easy for myself, and I just go from the starting position because I know that I don't have to work out distance. I only ever have to use displacement. All right. So if I just want to quickly work out this value over here, this displacement, well, that would be 25 minus 1.9, and that's going to give us 23.1 meters. Yep. So I can then work out the time, and the formula that I'll use, I've got the initial velocity. I don't have the final velocity, so I'm not going to use anything with final velocity. I'm talking about final velocity over there. So I'm going to use this one. Okay, so we're going to go delta x equals to v initial delta t plus a half a delta t squared. So, okay, and I will choose down as positive. Okay, so if that's my starting position, now my ending position is over here, so I'm ending below. Because I chose down as positive and I'm ending below, then this would be a positive value. So I'll say 23.1 because I'm just going from there to there. I'm not going all the way down. And my initial velocity will be negative 12 because I chose down as positive, but the ball initially goes up. Now the amount of time, that's what I'm trying to calculate. Gravity will be positive 9.8 because I chose down as positive, gravity's going down, and then delta t squared. So now we've got a trinomial. So what I'll do is I'll take this over to the right until we have a 0 over here. I'm going to bring this parameter to the front. So it's going to be 4.9 because that's half of 9.8. 4.9 delta t squared minus 12 delta t minus 23.1. Now, you're just going to use your quadratic formula where this will be your A value, here's your B, here's your C. And so if you had to work this out, you would end up with your time as, well, you'll get two answers. You'll get 3.72 seconds, or then you get a negative. Now, of course, we can't have a negative, but we'll write it down anyways. Okay, and then just say NA for that one. All right, so now it means, what that means is that to go all the way from there to there, it takes 3.72 seconds. Now I'm going to see how long does it take to go all the way to the ground, and then I can just minus those two values, and that'll give us how long did it take to go from the top of the door to the ground. So now my starting position is still at the same place, but now my final position is at the ground. Okay, I'm going to use the same formula. Let's say here, number 2, how long from start to ground. So that's going to be the same formula. I'll still choose down as positive. And so I'm ending below my starting position. So that's perfect because I'm choosing down as positive. So that'll just be 25 because I'm going 25 meters down. Okay, negative 12 once again. Delta T, we don't know. You might say, Kevin, isn't delta T 3.72? We just calculated that. No, that would be from the starting position to the top of the door, but now we're doing it all the way to the final position. Gravity will be positive, and then delta T squared. So once again, we're going to go and get a trinomial now. So 0 equals to 4.9 delta T squared minus 12 delta T minus 25 equals to 0. Let's just write that there. Okay, so once again, go use your quadratic formula, and you would get an answer of 3.79 seconds or negative 1.34. Now, of course, we can't have this one, so we'll just say NA. Okay, so it takes 3.72 seconds to go to there, and then it takes 3.79 seconds to go to there. So by minusing those two, by saying 3.79 minus 3.72, that'll give you 0.07 seconds. And remember that, so we said the answer was this, but depending on different methods and answers you got in the previous questions, I did see on the memo, this memo was actually quite thorough in they showed so many different ways. There was also like 0.08, for example. That's also going to be fine. Okay, so let's move on to this question now. It says, draw a velocity time graph for the motion of the ball from the moment it is released or thrown upwards until it hits the ground. Use the ground as the reference. Okay, so with a velocity time graph, we do that, and then we've got time on the x-axis measured in seconds, and then we've got velocity on the y-axis measured in meters per second. All right, now it says, clearly indicate the following: the velocity with which the ball is thrown upwards, the time taken to reach its maximum height, which we said over there, and then the velocity with which it strikes the ground, and we got that over there. Okay, I'm going to show you two different graphs. If you're a student that chose upwards as positive, okay, so the first velocity is 12. Now look how easy this is. Is it 12 up or 12 down? Well, that's 12 up. So if you chose upwards as positive, you'll put a 12 over there. Okay, so you'll put it at 12. Oh, doesn't look nice. Let's put the velocity like that. And let's put 12. Okay, in a different color, I'll show you what the graph would look like if you chose down as positive. So if you chose down as positive, then your 12 would be a negative. So you'd put a negative 12. Okay, now the next thing they said is the time taken to reach its maximum height. Well, we know that that time was 1.22. So at 1.22, then what was the velocity at the maximum height? What is the velocity of the object when it reaches its maximum height? Well, the velocity there is 0. So we're going to have something like this on our graph at 1.22 seconds, a velocity of 0. That'll be the same on this graph as well. Okay, 1.22 seconds. The next one is, what is the velocity when it strikes the ground? Well, that was 25.18. But remember that now it's going 25.18 and it's going down. But on this graph, you chose upwards as positive. So that's going to be a negative 25.18. So negative 25.18. So your graph would look something like that over there. It's always going to be a straight line, actually, like that. Okay. And then if you chose down as positive, well then at this point here it is going down, so that's going to be a positive value. So positive 25.18, so that would be somewhere there. And so that's what the two graphs would look like. Now, they didn't say the time for that part, so we don't have to worry about that. And that's it. Trolley X of mass 1.2 kilograms travels at 8 meters per second east and collides with trolley Y, which is initially at rest. Ignore all friction effect. The velocity time graph below, or I've put it over there, shows the velocity of trolley X during and after the collision. Okay, so let's have a look here. This trolley was traveling at 8 meters per second, and they said that that was to the east. Okay, so east is positive on this graph. They're making east positive. Then it collides with another trolley. So you see how it slows down over here. So this part here is where they are busy crashing into each other, this part over here. Okay, and then once the crash is complete, it all settles again, and it carries on moving at 4 meters per second, but it's still going east. How do I know that it's going east? Because this 4 is still positive. If it was going west, it would have dropped underneath to the negative y-axis. Okay, and you would have had like a negative 4 here. Right, so do they tell us if the objects collide? I mean, do the objects stick together? No. The velocity time graph. No, they don't say anything there. Okay, so first question, state the principle of conservation of linear momentum. Before I go get the proper definition, let's quickly talk about this. The conservation of linear momentum is when you use this formula. M1v1 plus M2v2 initial. Your teacher might, some questions you might use A and B instead of 1 and 2 equals M1v1 final plus M2v2 final. So what it tells us is that the total momentum of the system, because remember this is momentum, so it says that the momentum of object number 1 plus the momentum of object number 2 initially, meaning before the crash, is equal to the momentum of object number 1 plus the momentum of object number 2 after the crash. So they say that the momentum, the conservation of momentum, so the momentum is conserved. So the momentum in the beginning is equal to the momentum afterwards. Okay? Now let's go get the proper definition. Here we go. In an isolated or closed system, you don't have to say both of those, you can choose one of them. It just means, by the way, if it's isolated or closed, it means that there's no other forces like friction or things like that. And that's also why they said here, ignore friction. There's no applied forces, nothing like that. There's just two objects crashing into each other or moving apart, but there's no friction forces and things like that. They said that in a system like that, the total linear momentum is conserved, or you can say remains constant. And that's why we said that the momentum on this side was equal to the momentum on that side. This question here says, calculate the magnitude, so that means only the size, not the direction, of the velocity of y immediately after the collision. Okay, so it's easy. You just say m1 v1, or no, we're not going to use 1 and 1. We're going to use x initially plus y initially equals to x final plus y final. Then choose a direction as positive. I'm going to choose to the east as positive. Okay, so the x mass is 1.2. It's a very easy formula, this. What is velocity x before the crash? Well, that was 8. And it's a positive 8 because they said it was east, and we chose east as positive. Now, the mass of trolley Y, 0.5. They said it was originally at rest, so that'll be a 0. Now, x, the mass doesn't change. What is the velocity of x after the crash? 4. This part here is during the crash. They're probably going to ask us things about that later, like force. There we go. And that's where we're going to use formulas like F net delta T equals to delta P and all of that stuff. That comes here. And that's where you need time. Hint, hint, nudge, nudge, wink, wink. So, and I haven't even done this question. Like, I'm literally doing it for the first time now with you. But you just, as you do these questions, you learn to see what they're going to ask. Alrighty. And then it says, Then the mass of y, 0.5, and then we don't know what its final velocity is. What I'm going to do now is just type this part on my calculator. That gives 9.6. Then I'm going to type this on my calculator. That would be 4.8. And then 0.5 velocity of y final. I'm going to take the 4.8 over. So we end up with 9.6 minus 4.8 equals to 0.5. And then if you minus these two, you actually also get 4.8 equals to 0.5 Vy final, or V of y. And then if you divide by 0.5, you end up with 9.6. And you don't have to give a direction because they said magnitude. So you just say that. This question says, what is the average net force, now listen carefully, that trolley X exerts on trolley Y? Okay, so it doesn't really matter. I mean, if you chose either way, you're going to get the same answer because of Newton's third law. But the correct way is they want to know what is the net force that trolley X exerts on trolley Y. So we're going to use trolley Y's information because we want to know what happened to trolley Y. So we can use this formula. Of course, there's other ways of writing that formula. You could write it like this if you wanted to immediately. It doesn't really matter. In fact, I'm going to do it like that. I'm going to divide the t onto the other side. And then there's other ways as well. I mean, we know that delta P is the same as M, and then in brackets VF minus VI. You could even write it as MVF minus MVI. You know, we've showed all these different ways of writing it. It's all the same thing. It's the same formula. It's not like you have to choose which one depending on the situation. It's the same thing. So in fact, let me just show you. This is from the memo. So on the memo, this is what they give us. So I just took this one, and then I just put this at the bottom. So we ended up with that. And then I'm going to replace the delta P with all of that. There we go. This F is a subscript, sorry. Okay, now we're going to do this on trolley Y because they want to know on trolley Y. They're talking about like what did trolley Y experience. So F net is what we are trying to calculate. So the mass of trolley Y is 0.5. Okay, I'm going to run out of space here. So it's 0.5. What is the final velocity of trolley Y? We got it as, where did we write it? I think we got 9.6. Yeah. Yes, 9.6. And we got a positive answer, so that was to the right. Oh, I should choose a direction as positive. 9.6 minus the original velocity, the original mass is 0.5, and the original velocity was 0, and then the time for the collision. Now this is the collision part. Like, how long did the collision last for? There. So you could say 20.2 minus 20.1, or you could just say 0.1 seconds. Now, if you go type all that in, it's 48 newtons. Now, I'm not going to give a direction because they said calculate the magnitude of. So it's just going to be 48 newtons. Last question says, is the collision elastic or inelastic? 5 marks. This is a absolute giveaway of 5 marks because if we've learned about elastic, inelastic, we should know that it's just a calculation that we have to go do. There's nothing challenging about it at all. All we're going to do is the following. I want you to think about before the collision, before and after, and I just want you to go calculate the kinetic energy of each object. So let's do the kinetic energy of X, and then we'll do the kinetic energy of Y. So we'll do X, we'll do Y, and then we'll do the total. And then we'll also do the same on this side. And then we'll just see if the total is the same for both. If it is, we call that elastic. If it's not the same, we call it inelastic. Okay, so we're going to go get the kinetic energy. Remember, that's what we do for inelastic and elastic, is we go get the kinetic energy. So that's half mv squared. So half the mass of X is 1.2. Its velocity there was 8. What's that going to be? 64 times 1.2. Okay, Kev, just use a calculator, bro. 38.4. And that is measured in joules. It's a type of energy, and it is a scalar, meaning that it has no direction. You do not put a direction for energy. Now, for object Y, its mass was 0.5. Its original velocity was 0, so this is just going to give us 0. Add these two numbers together, and what do you get? 38.4. So that is the total energy before the collision. Okay, now we're going to look at the total energy after the collision. So for object X, it was going at 4 meters per second. So that's 9.6 joules. And then for object Y, it was going at its final velocity we calculated as 9.6. And that is 23.04. Add these two numbers together, 32.64. Okay, are these two numbers the same? No, they're not. So that is inelastic. Inelastic. A 12 kilogram block is initially at rest at point A. At the bottom of a rough inclined plane, the block is pulled up the incline by a constant force F acting parallel to the incline. The block reaches point B, which is at a vertical height of 4.5 above the horizontal with a speed of 2.25. Okay, so it reaches B at a speed of 2.25. Okay, so it starts at rest, so it starts at 0 velocity, and then it gets to 2.25 once it gets there. The first question says, define the term non-conservative. So, if you don't mind, I'm actually going to take a bit of time now, and I'm really going to go into the details of non-conservative forces and conservative forces, and I'm going to explain the exact differences between them. So what we're going to do is we are going to divide our page into two halves, okay? And at this top part, we're going to explore conservative forces. The only conservative forces we have, or that we look at, is gravity. Then you've got non-conservative forces, and that would be all the others. Tension, or no, that's not the main one. Let's go friction. That's the main one we look at. Applied forces, tension. Okay, but this is the main one that we look at. Now, what I'm going to do next is I'm going to draw two different pathways. So I'm going to draw a squiggly pathway, like that. Let's actually go... No, wait. Hold on, guys. I've got something I'm trying to do here. Let's just do that. Okay, and then that's just going to be the ground level. There we go. Then we're going to have a nice straight pathway over there. Okay, now I'm going to do the same down here at the bottom. Okay, and then same thing over here. Okay, so let's quickly go, and now I'm just going to use a different color over here to divide our page up. So this is just the page divider, this line in green. So let's explain a few things now. So let's say we've got a ball over there, and then we've also got a ball over there. But let's say that the height is the same. So let's say this is 5 meters, and this is 5 meters. And let's say the initial velocity is 0, and the initial velocity 0. It's going to be exactly the same over here. This is going to be really cool, guys, so just wait for me. And then same height. Okay. Now, when we talk about conservation, or we're talking about conservation, and in that we get conservative and non-conservative. So we're talking about the conservation of mechanical energy. That's what we're talking about, the conservation of mechanical energy. Now, you need to know that mechanical energy is potential plus kinetic. Okay, so let's start over here. What we can see is that the object has a 0 velocity, so it only has potential energy. So as the object, oh, by the way, I should have mentioned that. Because this one there's only gravity, okay? So there's only gravity acting on this object. There is no friction over here. There is absolutely no friction over here. But in these scenarios, there will be friction. So there is friction. Okay, and then here there's no friction. So what happens is that as this ball begins to roll, okay, begins to roll, what will happen to its height? the height will become less. So what will happen to its potential energy? It will go down. So that over here, the potential energy will go down. What will happen to the kinetic energy? Well, the kinetic energy will go up because kinetic energy is all about velocity. Remember, potential energy is mgh, kinetic energy is half mv squared. So this one goes down and this one goes up by the same amount, so the mechanical energy will remain constant. Okay, so the mechanical energy is constant. Now, as the ball gets to here, over there, it's going to start going up. So what will happen to the potential energy? Well, the potential energy will begin to increase and the kinetic energy will decrease because it's going to slow down. But once again, your mechanical energy will remain constant. Now, as we go down this pathway, then your potential energy will decrease and your kinetic energy will increase. But once again, your mechanical energy is constant. Okay, now, so over here, mechanical energy remained constant. Now over here, the same thing will happen. As you start going down the hill, the potential energy will begin to decrease and the kinetic energy will begin to increase and your mechanical energy constant. Same thing over here, potential energy decreasing, kinetic energy increasing, but your mechanical constant. So what I want to show you now is that no matter what we made this pathway look like, whether we made it look like that or whether we made it look like that, your result at the end is going to be exactly the same. You're going to have the same mechanical energy in both scenarios because in both scenarios we started at 0 velocity and a height of 5 meters. Here we started at 0 velocities and a height of 5 meters. So there is no difference between the mechanical energy throughout these two pathways. No matter if this pathway is maybe a little bit longer, it makes no difference. So what we can say then is that the path does not matter. As long as the height that we're working with is the same and the initial condition is the same, then whether this one has squiggly lines or it could have been even more squiggly, it does not matter. The mechanical energy remains constant. So the path did not matter. The pathway does not matter when we are looking at conservative forces. Now, when we are looking at non-conservative forces, such as friction, applied forces, or tension, I'm going to use friction. Let's see what happens. So once again, we have the same starting scenario between the two. Now, let's see what happens. As we begin to fall, the potential energy will go down, the kinetic energy will go up, but the amount that the potential goes down and the amount that the kinetic goes up won't be the same because there's now friction involved, and what you'll notice is that the mechanical energy will actually begin to decrease. Okay, the mechanical energy will begin to decrease. There is energy being taken away. Now, as this ball is moving, as it goes up or down, friction is removing energy from the object and its mechanical energy is decreasing. So the mechanical energy is going down. Of course, we still have kinetic energy and mechanical and potential energy, that's busy going up and down depending on whether we're going up or down. But overall, the mechanical energy is just decreasing. So when we get to the bottom, mechanical energy has been lost. Okay, now the same thing is going to happen over here. You're going to have friction that is acting, and so your mechanical energy is going to decrease along the way. However, if we look at the length of the pathways, let's say, for example, that this one is longer because it's got all these ups and downs and things like that. Let's say that this one is 8 meters long, and let's say that this one is 6 meters long. Then, because this pathway is longer, and by the way, that would have been the same over here. Maybe this one would have been 8 meters and this one would have been 6 meters, but the length of the path made no difference to our outcome. However, in this scenario, the longer pathway, so the 8 meter long pathway, will end up will end up removing more mechanical energy because the friction force has a longer time or a longer length of path over which to act, whereas here it only has 6 meters available. Okay, so in summary, this pathway is with this pathway, it's a little bit longer. So the friction is going to have more distance over which to act. And so more energy, more mechanical, or the object will lose more mechanical energy. So there is a difference in what happens to the object in this scenario and in this scenario. So we say that non-conservative forces do depend on the pathway, whereas with conservative, the pathway did not matter. So now that we have that explanation on conservative, non-conservative, let's quickly go check the definition. So here we go. A force is non-conservative if the work done by the force on an object depends on the path taken. Now that's what we said. Non-conservative do depend on the path. Non-conservative depends on the path. Okay, so yeah, hope that makes sense. This question says, draw a labeled free body diagram for the block when it is pulled up the inclined plane. And it's for 4 marks. That is usually an indication of the number of forces. So we've got a applied force. I will show you on the memo just now all the different labels you could use, but I'm just going to use F. But there is going to be other ones that you could use over here. Okay? Then we've got gravity. Now, with gravity, a lot of learners, they will put it like this, which is absolutely fine, but I like to rather break it up into its perpendicular and its parallel component. So perpendicular, I'll say FG perpendicular, and then parallel. Learners will often ask me, Kevin, is parallel up or down? Well, parallel is always down. Always, always, always. It's always trying to make the object go down the slope. Okay? And then there's normal force. Now, you might say 1, 2, 3, 4, but that's not correct. The gravity counts as 1. So we still need 1 more, and that would be friction. They said it's a rough incline, and friction always acts in the opposite direction to where you're going. So there we go. So now we've got 1, 2, that counts as 1, so that's 3, 4, and that's where the 4 marks comes from. Just quickly from the memo, you see how you could have had it like this. So some learners like to do it like that. You could also say FG over here. I'll get that for you now and I'll show you. But there you've got your 4 forces. Or you can do it the way that we did it, where we broke it up into FG parallel. I just prefer this method, but you don't have to do it that way. And then lastly, here are all the accepted labels that you could have used. You can use W, you can use FW, you can use FG, you can use MG, you can use all of those different things. For the force, you could have said FA, applied force. You see, so they're pretty lenient with what you can do. You can use, so there you can have a look at that and you can decide which ones you like to use. For this question, it says, calculate the total work done on the block by the non-conservative forces when the block moves from A to B. Okay, well, we can literally just go straight to using this formula over here, because this is the work due to non-conservative forces. So it says the total work by non-conservative forces. So we just have to go plug all of this in. So it just means, let me go get you the formulas for these two. Or let me just write them down for you. Kinetic energy is a half mv squared, that is on the formula sheet, and then potential energy is mgh. So to go because a lot of you, I know you might have tried to go calculate the work for the friction, for the applied force, but we don't know what any of those forces are. We don't know the friction, we don't know the applied force. So that's why this formula is just going to be the most straightforward. So we need to go get, it says WNC. Oops, let's make some space here for ourselves. Or let's do it here. Here. WNC is going to be equal to, okay, so it's the change in the kinetic energy. So it's going to be the kinetic energy at B. So half the mass is 12. The velocity at B is 2.25 squared minus the kinetic energy at point A which is 0. See, that's this part. Okay, all of that. Because it's the change in the kinetic energy, plus, now it's the change in the potential energy. So it's going to be mass, which is 12, gravity 9.8. The height at point B is 4.5, minus 12 times 9.8. The height at point A is 0. So that is all of that. So let me quickly show you something. This part is that, and this part is that. So you can just go ahead now and type it in on your calculator, and we get 559.58, and that would be in joules. And with energy, you don't give a direction. Okay, so we've done 5.1, 5.2, 5.3. So we've got 559.58. 559.58 joules. The same force now moves the block at a constant velocity across a... Oh, okay, now we're moving on to a different part of the question, I see. The same constant force now moves the block at a constant velocity across a rough horizontal surface from B to C, as shown. The force acts parallel. The magnitude of the friction force is... Oh, wow, this is going to be quite interesting. The magnitude of the friction force acting on the block while moving from point B to C is 42 newtons larger than the magnitude of the friction force acting on the block when it moves from point A to point B. Calculate the distance from A to B. Wow, okay. So if you read that and you're like, okay, that looks pretty challenging, I agree with you. That does look very interesting. I'm actually very excited about this question. I have, in all my years of teaching, I've never seen a question that asks it in this way. Okay, so I think we're maybe going to get some type of simultaneous, but let's have a look here. I'm going to use F net equals to MA over here. So let's just say here from B to C, I'm going to use F net equals MA. Now, the only forces acting on that object is there's this force, there is a friction force, there is gravity, and there is a normal force. So the only forces there's no parallel when you are on a flat surface. So I'm going to use these two in my F net equals to MA. So I'm going to say F minus F, well, F applied, but we'll just call it capital F like they have, and then small f for friction. Okay, and let's actually, okay, no, that's fine. So we're going to go F minus F equals to, now the mass is 12, but the acceleration is 0 because we are moving at a constant, where did they tell us? Constant velocity for that part. So the applied force is going to be the same as the friction force. Okay? Now, they told us that this frictional force is 42 newtons larger than the frictional force over here. So what I could then do is I could say, okay, I know that this is the friction from B to C, for example, from B to C. But what I can say is that the friction from B to C, let's do that with a normal F, the friction from B to C is 42 larger than the friction from A to B. So the way that I would write that mathematically is like this. What I'm saying is that this friction from B to C is the same as AB, but then you must plus 42. Can you see that that means that the BC is 42 larger? So what I'm going to do now is I'm going to replace this, or I'm going to then say, therefore, this is equal to the friction from A to B, plus 42. See, I just replaced this part by using this equation. And so now this is an equation that I can now use when I look at this part of the motion. Because now I've got a relationship between this force and this friction from there. Okay, that's going to help us. Okay, now something that's quite interesting. They asked us in the previous question to calculate the work due to non-conservative forces. And remember, non-conservative forces are things like friction, tension, and applied. Now, we don't have tension. So the only non-conservatives is friction and applied. So what we can say then is that the work due to friction plus the work due to the force applied must be equal to 559.58, because that's what we learnt about in the previous section. What we can then do is we can then go find the formula for work. Remember on our formula sheet, the formula for work is F x cos theta. So I can then go use that formula for each of these two things over here. Just wanted to clear some space over there. So we could then say that, so I'm now going to use this formula, which is the formula for work, on this one over here first. So that means I'm going to replace the F with friction, delta x cos theta, plus, now I'm going to use this formula over here. So that's going to be the force, delta x cos theta, and that's equal to 559.58. So we don't know, okay, let's go fill in what we do know. So we don't know what the friction force is, we don't know what the distance of the slope is, but we know that this will be cos 180. Why? Because the object is moving this way, but friction acts that way. So that's a 180 degree angle between them. Then we can say F over here, and then delta x, and then this one will be cos 0, because the object is going this way, and friction is also going that way. And then that's going to be equal to 559.58. Sure, so this is quite interesting. Okay, so now we've got this equation, and we've got this equation, but there's three unknowns. There is friction, force, and the displacement. Alright, so after sitting and looking at this for a bit, I realized there's actually a sneaky little trick we have to do here. Wow, okay. So we know that cos 180 is -1, right? So this whole thing is just going to become negative x delta x, because that's a -1. Then cos 0 is just 1, so this is just going to become f delta x. Okay, and remember, this is the friction of AB. This is the friction of AB. So what I'm going to do now is take out a delta. Well, actually, I'm just going to switch these two around, because when you plus, the order doesn't matter. I don't need that anymore. So we're going to say F delta x minus the force of AB delta x, like that. I'm then going to take out a delta x as a common factor, and you'd be left with F minus FAB equals 559.58. So check this out. I'm now going to take this FAB to the other side. So you end up with F minus FAB equals 42. So now, this is crazy. I've never seen something like this before. This part is this part. So I can replace it with 42. So we actually just got rid of two variables over there. So we can then say that delta x multiplied by 42 is then equal to 559.58. And look at that. Delta x is 559.58 divided by 42. And that'll give us 13.32 meters. A learner investigates the relationship between the observed frequency and the frequency of sound waves emitted by a stationary source. That sentence there has so much that I would like to talk to you about quickly. So, if you have a, because we need to know what is the difference between observed and the frequency. So what we have, let's say for example, we have a ambulance siren. So here's the siren. And it's making a alarm sound. Okay, that's the siren. Now, if you were just standing next to the ambulance and the ambulance is not moving and you are not moving, then you are going to hear the same frequency that the siren produces. You will hear, or in that case, okay, let's quickly say something here. So the siren produces a frequency. Now, as I said, listen carefully. If you are standing next to the police siren, or the ambulance siren, and you are not moving, and the ambulance is not moving, so there's no relative motion between you two things, the siren and you, then you are going to hear the same, the observed frequency, which is the frequency that you are observing, will be equal to the frequency, the produced frequency that, let's call this the frequency of the source. So the observed frequency, which is the one that the listener, remember the one that is observing is called the listener. So that frequency will be the same as the frequency of the source, or that the siren is producing. They will be equal to each other. But as soon as one of the objects begins to move, or both of the objects begin to move, then what happens is that these sound waves are either going to become more compressed, or they're going to become stretched out. And suddenly, these two things are not going to be the same anymore, and that is where we start using formulas like this one over here. Okay, so I hope that makes sense. As soon as we begin moving and things like that happen, then these two things are not the same. So the observed frequency is the frequency that you are listening to, and the frequency is what it really is. It's what it really is. Okay? What is the siren actually producing? And then this one is, what am I actually hearing because of the movement between the two objects? So this one here is not the real frequency. It's just the observed frequency after the waves have been compressed or stretched out because of motion. Okay. Now, the learner moves towards the source. Okay, the learner moves towards the source. So you should already begin to realize that, well, let's just see that they don't say something else. Towards the source at a constant velocity and records the frequency for a given source. The process is repeated with the move. Okay, so the learner is going to be moving towards the source. Okay, so if here's the person, now this person's going to move towards. So remember, there's waves being produced, sound waves. But if you are going towards, then you're going to make these sound waves become more compressed. So you're going to get something more like this. Well, let's do it a bit better. Can you see that they are more compressed? So we say that the frequency that the listener hears is going to increase. Or it's actually going to be larger than the frequency of the source. It's going to be larger because the frequency of the source is producing waves like that. But as soon as the person walks towards them, it makes them more squashed up. And so this person's ear is going to be detecting more sound waves per second. And by definition, that means a higher frequency. This process is repeated for different frequencies. Okay. The graph below shows how the observed frequency, FL, changes as the frequency of the sound waves emitted by the source changes. Oh, okay, so what they're saying here, so this is actually a bit of an interesting, it says here the process is repeated for different frequencies of the source. Okay, so they're changing the siren frequency. So they're starting off over here, for example, and then if you look at the frequency that the listener is hearing, that would be over there. And then they increase the frequency of the siren, and then this is what the listener is listening to, and then they increase it even more, and then that. So all they're doing is they're just measuring the frequency of the siren on this axis, and then they're measuring the frequency that the listener observes on this axis, and then they're just repeating that many times to create a graph. It says, name the phenomenon illustrated by the graph. Now, whenever they ask these questions, name the phenomenon or what is being described here, this is all considered to be the Doppler effect. This question says, name one application in the medical field. Okay, so they sometimes will ask this, but it'll never count a lot of marks. This one only counts 1 mark. So you must just know your different applications, but don't go into the details of how they work. So one of the things that, okay, so I'm not talking about the medical field now, but one of the things that we use the Doppler effect for in real life is speed cameras to measure how fast a person is moving. For example, in a car. For example, if you have a car over here, and this car is going this way, and then you've got a camera. So let's say we've got a camera over here, and this camera is busy detecting how fast the car is moving. The way that it does that is it sends out a frequency, and then if the car is going towards it, it'll cause the frequency to compress, something more like that. This machine can then measure this frequency over here, and from that it can do some calculations, and it can work out how fast is that car moving towards it, and that's how they work out if you're speeding or not. Now we can do something similar in the medical field to measure the speed of how fast our blood is flowing in our body. So let's say here, measures blood flow. This question, write down the type of proportionality that exists between FL and FS as illustrated on the graph. We get 2 types of proportionality in mathematics. Remember the words directly proportional, inversely proportional. Well, directly proportional is when you have a straight line, and then inversely proportional is when your graph looks like that. Now, mathematically, start with the y-axis. So you would say that FL is proportional, directly proportional to Fs. But if it was like this, you would say FL is proportional to 1 over Fs, if it was like that, okay? So we are going to say FL is proportional to Fs. This question says the gradient of the graph is obtained to be 1.06. If the speed of sound is 340, calculate the velocity at which the learner approaches the source. Now remember, it is a stationary source, so the source is not moving. So this is going to be quite a cool question. Check this out. So we know from our formula sheet that we've got the Doppler effect formula, okay, which says the following. Now remember, I have explained this in previous videos. You need to know whether to use a plus or a minus and a plus or a minus. If the one is a plus, the other one's a minus, and vice versa. But we need to know. So what I've told you in previous videos is, if the objects are getting closer, then you use a plus at the top and a minus at the bottom. If objects moving apart, then use a minus at the top and a plus at the bottom. So we're going to use this one over here. So we're going to put a plus at the top and then a minus at the bottom. So let's go fill in what we do know. What we're trying to calculate is the velocity of the listener. So that's this one, okay? They tell us that the speed of sound in air is 340. So we can go fill that in. So 340 plus velocity of listener is what we are trying to calculate. The velocity of the source will be 0 because they said it's a stationary source. And then the frequency of the source we also don't know. So it looks like we have 3 unknowns, but they told us that the gradient of this line is 1.06. Now gradient is change in y over change in x. They've told us, so that's going to be change in frequency of listener over change in frequency of source, because that's the y-axis, that's the x-axis. But because we're starting at 0, 0, we could use 0, 0 as one of our points. So then when you say change, you can actually just do it like that. Because you could imagine, if we were looking at this point over here, you would, okay, let me try to explain that for those of you that really want to understand that. So we've got that at the moment. Now let's say this point, for example, was, I don't know, 3, and let's say its x value is 3 and its y value is 4. Then you could use this as 0.00. So then you could say 4 take away 0 over 3 take away 0 for the gradient, right? But because this is 0, it just cancels out. And so we can actually just end up using that one little point over there to get our gradient. So we don't even need to use change, really. That's what I was trying to say. So they told us what the gradient is. It's 1.06. So we can just say 1.06 for FL over FS. So now we need to get FL over FS. So I'm just going to divide FS to the left. So we end up with FL, sorry, it's a small f, I keep switching it. FL over FS. And then here we just have 340 plus VL over 340. Now this we can substitute as 1.06. And then we've got this. Now remember guys, you cannot cancel these two because you've got two terms at the top. You can only cancel if you have one term at the top, one term at the bottom. Okay, so the way that we'll solve this now is you could multiply this 340 over to that side. Sorry guys, I have run out of space, so I'm just going to carry on over there. Okay, so you would end up with 1.06 multiply 340 equals 340 plus, okay, no, that's not going to work either. 1.06 multiplied by 340 equals 340 plus VL. Oh no, we don't even have anything at the bottom. There we go. Okay, so we could go multiply these two together now. And we get 360.4. And then here we've got 340 plus VL. Okay, and then if you take the 340 over, you end up with 20.4. Let's put the units, 20.4 meters per second. Okay, this last one says that, or let's just write that answer down nicely, 20.4 meters per second. Okay, copy the graph above in your answer book and label it as A. On the same set of axes, sketch the graph that will be obtained when the learner is moving at a higher velocity. Okay, very easy. I'll show you what to do. So they asked us to label this as A. Now, remember that the gradient was FL over Fs, and they said that that was 1.06. Now, the source is not going to be moving, so that stays the same, but they said that the learner is going to move at a higher velocity. So the y part is going to become larger. So what will that do to your gradient? Well, if you have delta y over delta x, if you make this larger, then the whole fraction becomes larger. So the gradient, because remember this is the gradient, will become larger. So you're just going to get a graph that does that. A charged sphere, M, suspended from a ceiling by a inextensible insulated string, another charged sphere N of mass 2.04 times 10 to the negative 3, and carrying a charge of that hangs stationary. Okay, so this one here we have its mass as 2.04 times 10 to the negative 3 kilograms, and we also have its charge as 8.6 times 10 to the negative 8 coulombs. Hangs stationary vertically below sphere M. The centers of the spheres are 0.3 as shown in the diagram. First question, Coulomb's law. Now before you go try to remember definitions, write out the formula for Coulomb's law, which is this one. And so what we should expect is that it's going to say the following. The electrostatic force between two charged spheres is, now when something's at the top, we say directly proportional. So directly proportional to the product, because these two are being multiplied, of the charges. And when something's at the bottom, inversely proportional to the distance between the centers squared. Or they might say to the square of the distance between the centers. Okay, let's go get the proper definition now. So let's see. The magnitude of the electrostatic force, this one, by 1 point charge on another is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. How cool is that, guys? The formula tells you the definition, so it makes it a lot easier to memorize or to remember in the exam. This question says, state whether the charge on M is positive or negative. Okay, that'll be very easy to do. We can see that this charge N over here is a positive charge. Remember, they told us over here that it's positive. Now, can you see that there is nothing holding this N? There's no like stand over here. So this thing's literally just floating in the air. Why is it doing that? Because there is gravity trying to pull it down. The reason is that this charge over here must be attracting it upwards. So the fact that these two are attracting each other means that if this one's positive, this one has to be negative. So we'll just say negative. This question says, draw a labeled free body diagram for N. Now, it's for 2 marks. Now, that usually means there's only 2 forces. So let's see. We've definitely got gravity. Now, you can call that W. There's a whole bunch of different things you could call that. And then we're going to have a force upwards, which is the force due to M. So I'm just going to say it's the force due to M. Now, I'll quickly show you on the memo. There are so many different labels you could have used here. So here we go. Okay, they used FE, but instead of FE, you could have used F electrostatic, just F, FM on N. I just used FM. And then they used W, but you could use FG, W, MG, gravitational force. You see, there's a lot of options. So I've often had learners saying, yeah, sir, but my teacher doesn't do it like that. So you must be wrong. But it's different in different, this is the official memo, and so different schools do it differently. I wish there was only one way, so there was never any doubt between us whether we can do that one or that one. We could have just learned one, but I guess as times change, more things get introduced. Suddenly we have a whole collection of things we can use. This question for a good old 5 marks. Calculate the magnitude of the charge on sphere M. Right. Very easy question, actually, guys. What we can do is the following. We know that this object is not moving. Now, I don't want to just assume that. I'm sure they've told us that. Another charged N carrying hangs stationary. There we go. So what we can do is we should understand that if this object N is not moving, then what does it mean for these 2 forces? They must be equal to each other, right? So we can say that Fm must be the same as Fg. You could have also said F net equals to MA, but A will be 0, and then you would take it over. Okay, now we can then say that Fm, which is the charge between them, is going to be equal to this, which is mg. So that's mass, which is here, 2.04. Okay, I'm going to run out of space here. So let's say Fm equals 2.04 times 10 to the minus 3 times by gravity, which is just 9.8. Now, if you go calculate this, and if you round to 2 decimals, this will be, oh, not a nice number, 0.02, and that would be measured in newtons. Okay, so now we know the force of M on N, but we know from Newton's third law that Fm on N or Fn on M or Fm on N, it's the same thing. So we could now just go use the this formula over here, right? Because we know the force between them now. K Q1 Q2 over R squared. We've calculated the force, so that's 0.02. K is just a constant that you get on the formula sheet. It's 9 times 10 to the 9. Q1, we can just make that Qn, for example. They told us over here, 8.6 times 10 to the negative 8. And then, let's get rid of all of this now. Q2, we can just call that Qm. That's what we're trying to calculate. And then the distance between them is in meters. That's good, 0.3. And then don't forget square. All right, and now to solve this, there's different ways you could do this. I am just going to... So I think in a test, what I would do is I would show them. I'll take this over to that side by multiplying, and then I'll take these 2 over to the bottom by dividing. So we're going to end up with 0.02 multiplied by 0.3 squared over 9 times 10 to the 9 times 8.6 times 10 to the minus 8, and that's all equal to Qm. Go ahead, type that all in on the calculator, and we get ugly looking answer, but it's Qm equals 2.33 times 10 to the negative 6 Coulomb. Now, okay, so we've got that now. Now this question says, how does the electrostatic force that M exerts on N compared to that exerted by N on M? So the magnitude will be the same. Now the direction, okay, well, let's just see, how does the electrostatic force that sphere M exerts on, so we can just say in opposite direction, in opposite direction. What do I mean by that? Well, this one exerts a force down on M, and this one exerts a force up on N. Alright, so then the last part says here, point X is 0.1 meters vertically below the center of N, as we can see over here. Calculate the net electric field, that means E, at point X. Okay, very easy. We've done questions like this before. Usually I show you questions in the horizontal direction like this, where, for example, you have A and you have B, and then you've got distances like 0.2, 0.3, and then they'll say calculate the net electric field at X. Now, X is not a charge. X is just a random point. So remember that when we have a random point, we will assume that it is positive. That is from just the definition that we've spoken about in previous lessons. We always assume that that part is positive. Now, all that we go and do is calculate the E value, or the electric field, between A and X, and then B and X. And then we just plus or minus depending on the directions and the charges. But we never look at A on B. We're not interested in A on B. Okay, so it's a very easy question. It's a guaranteed 5 marks. So now we're just doing it in a vertical direction. Okay, so we've got M, N, and X. So let's just go draw it out here. We've got M, we've got N, and we've got X. Now, we're going to use this formula over here, KQ over R squared. Now, we also know that this distance here is 0.1 meters. And then this distance here is 0.3 meters. So let's start with, you can start with whatever you want, but I'm going to start with N. So I'm going to start with the electric field of N on X. And so that's going to be equal to 9 times 10 to the 9. Then the charge that you use is not the charge of X. X isn't even a charge. X is just a point. So you use the charge of N, which we did have earlier as 8.6 times 10 to the negative 8, and then the charge of and then the distance between those two is 0.1. Don't forget the square. And if we had to go work that out, let's see what we get. We get 77,400. Now E is measured in N dot C negative 1. Okay, now N is positive, and we said that by definition, X is also positive. So what will N do to X? Will it push it up or down? Well, it'll push it away because they're both the same, so they're repelling each other. So it would push X down. Okay, now we're just going to go and look at what is the effect of M on X. So now we're going to go to M on X. So we use the same formula, 9 times 10 to the 9. The charge of M we got over here, 2.33 times 10 to the negative 6 over. Now the distance between, now don't use 0.3, a lot of learners do that. It's from M all the way to X, so it's 0.3 plus 0.1, which is 0.4. And let's go work this out. That gives us 131,062.50 Newton Coulomb. Now, M is negative. Okay, we didn't put a negative over here because they just wanted the magnitude earlier. But I did look on the memo because I was just curious to see if they would allow you. If you did put a negative over here, that would have been fine. So, as we've said, m is negative, okay? So m is negative, x is positive, so they will attract each other. So what will m do to x? It'll pull it upwards. So we could say up. There we go. So now we know the value of this one and this one. One of them is going down and one of them is going up. So we can then say, now you can choose up or down as positive. I'm going to choose upwards as positive. So I'm going to say up is positive. And I'm going to say E net. So the net electric field is going to be 131,062.50 because that one's going up, minus this one, 77400. And that'll give 5. Whoa, that's not a 5. 53662.50 n dot c minus 1 up. The first thing I want to mention about this question is that it does carry on onto the next page, okay? So we've got 8.4 and 8.5 coming up as well. The circuit diagram below shows 4 resistors, 1, 2, 3, 4, connected to a battery of EMF E and internal resistance R. So there they are. The resistance of the ammeter and connecting wires are negligible, while the voltmeters have very high resistance. Okay, that's always going to be something. Now, state Ohm's law in words. So Ohm's law, there's a couple different definitions you could have used, but on the memo, the easiest one is this one. It is the ratio of the potential difference to the current. So let me show you what that means. R, if you had to take, the formula I equals to V over R or V equals to IR. If you get R by itself, it says that. So it says that the ratio of potential difference to current is a constant at a constant temperature. They tell us that switch S is closed. Okay, there it is. Now they say that the reading on the ammeter is 3.5 amps. First question for 4 marks. Calculate the total external resistance of the circuit. Well, step 1, you need to see what's parallel, what's in series. The way that we do that is you always start at the battery over here, and you keep going until there. Suddenly, the electricity can split. So some of it will go this way. The rest will go this way. It joins up again over there. And then carries on together. Notice that I didn't go this way because that is a voltmeter. And I didn't go this way because that's also a voltmeter. We don't go through voltmeters. So the parts in yellow, that is part of your main circuit. Then this part here, the blue and the green, that is in parallel. So yeah, the blue and green is in parallel. But now, well, let's rather say parallel. But now please keep in mind that this green pathway, these two will be in series. Okay? They are in series together. So what we will do is let's first go and combine these two together. So 3 plus 2 is 5. Let's quickly do that again. So what we would then have, you can imagine, is that you've got a 1 ohm over there. And then we've now combined this pathway into a 5 ohm. So that's what we now have. Oh, and then we have a 4 ohm over here. 4 ohm over there. Okay, so now what we can do is we will go and combine these two in parallel. So we know that the parallel formula goes like this. 1 over R1 plus 1 over R2. So that's going to be 1 over 5 plus 1 over 1. And so that would end up giving 6 over 5. And then what you do is you flip upside down and flip upside down. And so you end up with R parallel is equal to 5 over 6. Okay, so now we have the R parallel, so you could almost think of it as so now you can imagine that we have something like this. So we've got 5 over 6, and then a 4 ohm over there. And now we can combine those into series, and so that will be 5 over 6 plus 4. We don't need to put that, and that'll give us 4.83 ohms. 4.83 ohms. The next question for 3 marks says calculate the reading on the voltmeter. Well, this is an easy question because we know that voltage is equal to I times R, and as long as we can choose the right I with the right R, then it works. So we know that we've got this current. Now that current is part of the main circuit. So it's part of the total circuit. So when you're using that current, that is the main current in your entire circuit. So you will have to use all of the resistors in the circuit. So you'll use this resistance over here. So you will say V equals to I times R, which is then equal to 3.5 multiplied by 4.83. And that'll give you 16.91 volts. This question says, how does the reading on voltmeter V2, where's V2? Here, compare to the reading on voltmeter V1? It will definitely be smaller then, but let me explain. So, when you go to the shop and you buy yourself a battery, on the battery packaging, it will give you the EMF. Okay? Let's say no, I'm not going to give an example because some of you will think that's the value of the EMF. Let's say, for example, it was 20. Okay, I'm not going to write it down, but let's say it was 20 volts. When you plug it into your electrical circuit, the voltage that you actually get for your circuit is this one over here. And this one we calculated as 16.91. So it will be less than what the EMF is because some of the voltage gets wasted in the battery itself. Okay, now that voltage over there has to be used in the circuit. Some of it will be used over here, and then some of it will be used in the parallel. So because some of it is going to be used over here, then there will be less available for the parallel, which is the V2. So maybe if we use 4 volts over here, that's just an example, then you would only have 12.91 volts available for the parallel part. So this part here will have to be less than the V1. If this wasn't there, then they would be equal to each other. Then these two would have to be the same. But because of this device over here, which is going to take some of the voltage, then there will be less available for this one. Okay, so we're just going to say smaller. This question says, a learner concludes that the EMF of the battery is equal to the reading on voltmeter V1. That probably is not going to be true or it won't actually be true at all. Sorry, I forgot if there was an internal resistor or not. If there was no internal resistor, then this statement would be true. The EMF that you get on your battery is the same as what you actually get because there's no wasted volts in the battery. However, there is an internal resistor, so some of the volts will be wasted over here, so these two values will not be the same. Okay, so let's have a look. So it says define the term EMF. Well, to understand the definition of EMF, you need to remember one of the formulas for volts. We know volts is equal to that, but there's a different definition. It's equal to the amount of energy per charge. So voltage is the amount of energy per Coulomb of charge. But now when you are talking about EMF, you are talking about, remember, the EMF is what the voltage says on the battery. It's the maximum voltage you could ever get, but unfortunately we never get that because of this resistor. But it's the maximum that you could get in theory. So EMF is going to be the maximum amount of energy per charge. Now let's go get the proper definition. It is the maximum energy supplied by the battery per unit charge. Energy, charge. Okay, so that's that question complete. Now we are going to this one. Remember, there are still more questions on the next slide. Okay, so it says, is the learner's conclusion correct? Choose from yes or no. Definitely a no, and then give a reason. So we said that the learner would have been correct if there was no internal resistor, but there is. So we will just say that the battery has an internal resistance. Switch S is now removed and replaced by a voltmeter. Okay, so let's just quickly go back to the previous slide. You see how there was a switch over here? Now it's a voltmeter. So what that immediately means is that electricity cannot flow through here. This whole pathway is now blocked off. Electricity cannot flow through a voltmeter. Voltmeters have a very high resistance. And so what happens now is that we now have a circuit that's just going to go like this. Okay? And so let's see what they ask us. How will each of the following change? Choose from increase, decrease, or remains the same. The power dissipated by the 4 ohm resistor. Now, a lot of you might say nothing's going to happen to the 4 ohm resistor because it's not part of this over here, but that won't be correct. Let me explain in detail for you. Remember that when you have a parallel pathway, I don't know if you can remember this, but that actually allows the electricity to get around the circuit easier, because when there are more pathways available, it makes it easier for the electricity to flow. And I've often used this analogy. Imagine there are people that are walking into a shopping center. Now, if the shopping center only has one door, then you're going to get a whole lot of people and they all have to go through one door. That's going to take quite a lot of time. We will say that there will be a large resistance. But what if you have many doors? What if there is a door here, a door here, and a door here? Well, then what happens is that some people can go this way, some people can go this way, and some people can go this way. Would you agree that that would make it faster for all the people to get into the shopping center? So what we say is that the more doors you have, or the more pathways that you have available, so the more pathways that you have in parallel, the easier it will be for the electricity to flow, because the overall resistance actually becomes less. So Kevin, are you telling me that the more pathways you have in parallel, even though there's going to be more resistors, the overall resistance becomes less? Yes, that's exactly what I'm saying. I'll prove it to you. It's because of the way that the parallel formula works. Let's say we have two resistors in parallel. One of them is a 3 ohm and one of them is a 2 ohm. Then I'm going to show you what will happen if we have 3 resistors in parallel. One of them will be a 3 ohm, one of them will be a 2 ohm, and one of them will be a 4 ohm, for example. So if we use the parallel formula, 1 over 3 plus 1 over 2, if you work that out, you get 5 over 6, but then you have to switch it over, remember, because that's that. So then you would get R parallel is equal to 6 over 5, which is the same as 1,2 ohms. Now, if you have 3 resistors in parallel, 1 over 3 plus 1 over 2 plus 1 over 4, if you work that out, you get 13 over 12, but that's 1 over R parallel. So if you then had to switch that over, you get 12 over 13, and that'll be 0.92 ohms. So can we see that the more parallel resistors that you actually have, the lower the total resistance becomes? Look at that. See that? So the more pathways we have, the less the overall resistance. So if we block this pathway out now, what have we just done? Have we made it more difficult for the electricity to flow or more easy? Well, think about a shopping center. Here you had 2 pathways available. Now you've only got 1 pathway. So now you've only got 1 door available. So the overall resistance in the circuit is going to increase. So let's make some notes. The overall circuit resistance will increase. That means it's more difficult for the electricity to flow. That's like having it more difficult for people to enter the shopping center because there's less doors. Okay, so that means that the overall circuit current, this value here, will decrease. Meaning that, remember, current tells you how fast is the electricity flowing. If the overall resistance becomes more, then it's more difficult for the electricity to flow. So the overall circuit current will decrease. So now, if you had to go work out the power over here, you could say P equals to, okay, so we've got different power formulas. You've got VI, you've got I squared R, and then you've got V squared over R. Now we know that the R is 4, that doesn't change. And we know that the current is going to become less going through here. Because we said that the overall circuit current, which is the current that flows in the main part of the circuit, or actually now it's all in series, we said that that's going to become less. So the current in here is going to become less. So the overall circuit current will decrease. So if we then use this formula, we know that this is a constant and this is going to become less. So the power will become less. So the power will decrease. So we're going to say decrease over here. This one says, what will happen to the reading on the voltmeter? So we're talking, so the voltmeter reading that we had earlier. Okay, well, let's think about that. Now, this one's a challenge because, okay, I love this question. So check this out. We know a lot of learners are going to get this one confused because we know that voltage is equal to I times R. But what Kevin has just said is that the current in the circuit will decrease, but the overall resistance will increase. So some learners are going to say, oh, it'll stay the same. But we don't know if maybe the resistance increased by a larger factor than what the circuit current decreased. So you can't use this formula to answer this question. If you've watched my videos on this before, you would remember that the way you answer a question like this is the following. We take the EMF formula, we multiply it out, and then remember that this is the circuit voltage, the external circuit voltage. So that is your V1. That is your V1. So we're just going to group all of that together as V1. And then this part here, we can leave it as it is. So to calculate V1, you're going to end up with EMF minus IR. Okay, so the EMF is a constant. That doesn't change. We got to look at this part over here. Now, this part is amazing to analyze because this is a constant. That's your internal resistance. But we know what's happening to this one. We know that the overall circuit current will decrease. So what's going to happen to this value? Well, if this is decreasing, this is a constant. Sorry, this is a constant. Then this will become less. So then what will happen to this value? Well, you've got your EMF minusing a smaller value. So that means that this will actually become a larger value. You might just need to give yourself some time to think about that. So the answer is going to be increase. Now let's explain it, because they want us to explain it for 4 marks. So what we can say is the overall circuit resistance will increase. Overall circuit current will decrease. Then we can show them this formula. IR plus IR, and then this one, V1 plus IR. So we can then say, therefore, IR will, or let's actually first rearrange the formula to become V1 equals to EMF minus IR, and then we can say, therefore, IR, let's rather say, with circuit current decreasing, IR will become smaller. Therefore, V1 must increase. And remember that your EMF is constant. The diagram below, now I've put the diagram over there, shows the initial position of the coil in a simple DC generator. The coil is rotated anti-clockwise as shown. Name the component in this generator that ensures that the induced current in the external circuit is in one direction only. Well, it's this device over here. Because it's DC, this is called a split ring commutator. That's that question. This question, is the direction of the induced current from X to Y or Y to X? So here you have to use your, now remember you got to think about this. Do we use our right hand or our left hand for this one? Well, this is a generator, so we use our right hand. Now remember, I've showed you how to do this before. So you're going to take your right hand, you're going to take your index finger, which is the one next to your thumb, and you're going to point from north to south. So you're going to point to the right. Then you're going to take your thumb and you've got to think about, what is XY about to do? Is XY about to go down or is XY about to go up in the rotation? Well, it's about to rotate down. So take your thumb and turn it down. So right now your hand should be looking pretty weird, where you've got your index finger pointing from north to south. You've got your thumb pointing down. Now what is your middle finger doing? Is it coming out of the page towards you or is it going into the page? Well, if you've done this correctly, it should be coming towards you. So it should be coming out of the page. So we will say Y to X. This question says that a maximum voltage of 90 volts is generated when the coil is rotating at a frequency of 20 Hertz. Write down the time taken for the coil to complete one rotation. Okay, so we know that there is a frequency of 20. What does that mean? It means, frequency is number of cycles or rotations per second, or let's say per second, per second. So that means that this thing is rotating 20 rotations per second. But that's not what they want. They want to write down the time taken to make one rotation. So if we can do 20 rotations in a second, they want to know how many seconds does it take to do one rotation. So they are actually asking us for the period, because the period is number of seconds per one rotation. So they want the period. So we know that period, which is a t, is 1 over frequency. So we're going to say 1 over 20, and that'll be 0.05 seconds. Or we can just say s, like that. So the answer will be 0.05. That is how many seconds it will take to do one rotation. So then in a whole second, it'll be able to do 20 of them. This question says that the coil starts rotating from the initial position as shown in the diagram. Haha. So remember, I have showed this in the electrodynamics videos, where when you're drawing the graph, you need to look at the starting position or read what they say to see whether we have a what did I call it? A peak or a zero or something like that. Okay. So it says that the coil starts rotating from the initial position as shown in the diagram below. Oh yes, that's what I said. Parallel, perpendicular, peak, zero, something like that. Now, sketch a graph of output voltage versus time for one rotation. Indicate the maximum voltage and the time value. Okay, so we know that one rotation is going to be after 0.05 seconds. But let's just put here time measured in seconds and then voltage measured in volts. Right, now we're going to either get a graph that does that or, wait, 1, 2, 3, 4, 5. Remember, I always said there's 5 parts. 1, 2, 3, 4, 5. It's either going to do that. Remember, we're not going to go underneath because this is a DC and not a AC. Right. So what we've learned is that if we draw magnets north and south, if you start over here, then that is a peak. That starts at a peak. If we, and that's where the coil is, it's parallel to the magnetic field. Now, if we have something like this, where it starts perpendicular, then we call this a zero. So here we can see that we are starting in this perpendicular position. We are perpendicular to the magnetic field. So we're going to start at the 0 position. And then we're going to just do 5 things. So 1, 2, 3, 4, 5. Let's just double check. 1, 2, 3, 4, 5. There we go. Remember the 5 thing I did speak about when we were teaching this in the lesson videos. And now we just need to give the voltage. They said 90 volts, so we just put 90 over there. And 0.05 would actually go over there. And then I guess we could also put the halfway mark over there. I doubt they would want that, but let's just do that. So that'll be 0.025. 0.025. Wall sockets supply RMS voltage and current. A 220 volt AC voltage is supplied from a wall socket to an electric kettle having a resistance of 32. Calculate the energy dissipated by the kettle in 2 minutes. On our formula sheets, these are the different formulas that we could use. Now, they want average energy dissipated, so we're going to use, I'll use one of these ones because that is energy over there. And then we might have to use some of these ones as well. But let's just see what we have. So they're giving us a 220 volt AC voltage. Now, that's going to be RMS because they said that they said that wall sockets supply RMS. So this is a RMS value. And we have a resistance. So let's just have a look. Calculate the average energy dissipated. Yeah, so we could actually just go straight and use this formula. When we use this formula, we will use an RMS value over here. And so W, which is energy, is equal to 220 squared. The time is 2 minutes, so we'll say 2 times 60 because it must be in seconds. And then the resistance is 32. And that'll give us 181,500 joules. Light is incident on the cathode of a photoelectric cell connected to a battery and a sensitive ammeter as shown below. So we know that this is the photoelectric effect. If you take light and you shine it onto the surface of a metal, then electrons will be released and then they can flow around the circuit. So it says, what conclusive evidence about the nature of light is provided by the photoelectric effect? Well, the photoelectric effect tells us that light consists of a particle nature, because we know that if you have a metal over here, we know that these individual electrons get released when the light hits the surface of that metal. And so what scientists observed is that light doesn't only travel as a wave, like some theories tell us, but also as particles. Remember, we said that each of these things from the light is a photon. So we can say it's the particle nature of light. Light has 2 natures, a wave nature and a particle nature. The photoelectric effect helps us to determine the particle nature. The cathode has a work function. Okay, remember the work function? I have explained this in detail in the previous in lessons. So we should all know what work function is. It's the amount of energy that you need to remove an electron. Oh, they're asking us to define it here. It's the minimum energy needed to eject electrons from the surface of a metal. Okay, so moving on, it says light of frequency 5.96 times 10 to the 14. So that's the light itself, 5.96 times 10 to the 14 hertz, is shone onto the cathode. Calculate the maximum kinetic energy of an electron ejected from the cathode. So for this chapter, we've looked at all these different formulas, okay? So we know that the frequency of the light. So we could then use this formula to calculate the energy of the light and then put it into that formula over there. So we could just say E equals work function plus EK maximum, and we could replace this with HF. Okay, I've explained this in the lessons, guys, so you must just have a look at that if you don't know this chapter too well. And then work function plus EK. So we can go use Planck's constant now. Now this is just Planck's constant that you get on the periodic, not on the periodic table, but on the formula sheet. 6.63 times 10 to the negative 34. Then the frequency of the light is 5.96 times 10 to the 14, and that's equal to the work function, 3.42 times 10 to the negative 19, plus the EK. Okay, so now I'm just going to go type all of this on the calculator, and then I'm going to take this to the left. And we should end up with EK as 5.31 times 10 to the negative 20, and kinetic energy is a type of energy, so it's in joules. And so, okay, that one's done. Now it says that the ammeter registers a current of 0.012 amps, 0.012 amps. Calculate the minimum number of photons of light that strike the cathode in a 10-second period. Well, one of our formulas for current is equal to charge divided by time. So we could now take the current, which they've given us, and the amount of time, and we could work out how much charge is coming past. Okay, so you would use the formula as I multiplied by T equals to charge, and so the current is 0.012, the time is 10 seconds, and so if we're to work this out, we get 0.12 coulombs. Now, we know that the charge that is coming past is actually electrons. So you could then use this formula to see how many electrons. So this is the charge, which we've just calculated. And this is the charge of one electron, which is on our formula sheet. And then this is the number of electrons. So we could say N equals to Q over E. And so the number of electrons will be 0.12 divided by. Now the charge of an electron is given to you on your formula sheet. It's 1.6 times 10 to the negative 19. And that'll give us 7.5 times 10 to the 17 electrons. So it says how many photons of light do we need? Okay, now remember, in the light, there's little individual packets over there, which are called photons. Now, when one photon hits the surface, one electron gets released. So if this is how many electrons are released, then that is also how many photons we need. So 7.5 times 10 to the 17 photons. Then this last question says, the intensity of the light is increased. So when you change intensity, what it means is that there will be more photons. Okay? So that means that there will be more electrons being released. So if you have more electrons being released, you would have more charge, and so the current would go up. So it says that how will this change affect the ammeter? Choose from increases, decreases, or remains the same. So we'll say increases. And then we can say a larger intensity means more photons available, more electrons will be released per unit time, increased ammeter reading.